Optimization problems, part 2. Essential question, how do I use derivatives to maximize and minimize some aspects of a situation? Let's take a look at finding the area of the largest rectangle that can be inscribed in this semicircle. So we can see that here's our rectangle, there's symmetry here, and that this distance is x and this distance is x. So when we find the area, it'll be 2x as the length and y as the height. Let's go ahead and write down the beginnings of how to do the problem. We want to find the maximum area, and we know the area is 2x times y. And we also know this is a semicircle, x squared plus y squared is equal to r squared. So when we solve for y, we're going to be able to put that into our y, and we get this expression. Let's go ahead and find the derivative, and I'm going to have to use the chain rule. Also, the domain is going to be from 0 to r, but neither 0 or r are going to be solutions that I want to use because they won't create a rectangle. They'll be a flat rectangle. Okay, here's the next step in which we go ahead and simplify the derivative. So I get this derivative and I have a common denominator, and then I simplify. So I'm going to get this as my numerator. And the only way a fraction can be equal to 0 is if the numerator is equal to 0. So when I look at setting the first derivative equal to 0, I'm really only concerned at using the numerator. When I solve, I'm going to get this as my critical point. Now I'm going to use the first derivative test in that I'm going to use a number before r and after r. And when I use x equal to 0 right here, if I use x equal to 0 into this numerator right here, I am going to get a positive value here. So x is equal to 0, this is going to be positive value, and this will be positive. Now I'm going to check out 0.9r, and when I choose 0.9r, because I can't really choose r will be a 0 down here. But if I choose 0.9r here, and I'm going to get this numerator being negative. So by the first derivative test, a prime changes from positive to negative, which implies a maximum value. Now to finish the problem, I need to go ahead and answer the question which says to find the area of the largest rectangle. So here's the formula, 2xy, and I know that y is equal to r squared minus, and now that I have an x value right here, I'm going to use this as my x value. I'm going to get r over root 2 for my y value, and then when I simplify, I'm going to get r squared. Now there is another way to do this problem. If you want to take a look at, do it in terms of the angle. If you do it in terms of the angle, then this is the radius, and this will be r sine of theta and r cosine of theta. And the area will be actually the x length, which is 2 of these, so it's 2r cosine theta, times the y, which I'm calling r sine of theta. So I multiply everything out, and this is an identity. If you recognize this identity right here, you can simplify it to this so that the derivative process isn't so difficult. I'm going to take the derivative, and I'm going to get this value, and when I solve for cosine of theta, it's really this part that's going to make the whole expression 0, and that's only going to happen when theta is equal to pi fourths. I'm going to take the second derivative, and I get this, and when I evaluate the second derivative at pi fourths, it is negative, which implies the maximum value. Again, I'm not going to worry about an interval. The interval would have been 0 to r, but neither of those values would have given me an area of a rectangle. It would have been a collapsed rectangle. But the question just does ask for the area, so I go back to my area formula, and I put pi fourths in for the theta each time, and I get these values, and I still get the same number. Okay, the next one is a cylindrical can that can hold 1 liter of oil. Find the dimensions that'll minimize the cost of the metal to manufacture the can. So it's really asking for the minimum surface area. So that's what we're trying to find, the minimum area but in this case it's the surface. Now the surface is comprised of two circles and the lateral area, and the lateral area is base, which is 2 pi r around the circle circumference, times the height h. Okay, so let's take a look at this. So the area is 2 pi r squared plus 2 pi h. Now remember that the volume is equal to pi r squared h, which is 1,000 cubic centimeters, because it's 1 liter of oil, which will allow me to solve for h. Solving for h means I'm going to be able to substitute it into my area formula and get the area in terms of r only. And when I simplify it, I get this. And this will be 2 pi r squared plus 2,000 r to the negative 1 power. And this is what I'm going to be taking the derivative of. Okay, next step is to actually take the derivative, and this is 4 pi r minus 2,000 r squared, and we want to get a common denominator, and it's the numerator that's going to make the derivative 0, and when that happens, r is equal to this. I want to use the first derivative test, and I know this is the critical point, cube root of 500 over pi, and I want to test a point before and I want to test a point after. That's what they're talking about right here. And so they observe that the derivative is negative when it's less to this quantity, and it's positive when it's greater than this quantity. When that happens, this is the first derivative test, that means we are going to be getting a min. But you must state to the AP people, you must state it that the derivative is changing. You can't use the sign chart as justification. All right, so we don't have to use the closed interval test because the values for minimum and maximum on the for the lowest interval and the highest number in the interval will not create a rectangle. So we know this is going to be the absolute min. Now the question also asks for the dimensions. So knowing that r is equal to this, we got to substitute in for h, and when we substitute h, we get 2r. So these are the dimensions. R is equal to this, and h is equal to this.